Hi friends, I'm P.THIRUMENI, M.TECH Embedded System student from VTP Technical University. Now I am going to explain about my M.TECH project. The title is Avionics Full Duplex Switched Ethernet, that is AFDX, Protocol Stack Development for Remote Data Concentrator Implementation. This is an avionics related project. Let me give some introduction about my project. Today's digital world, every computer and most of the devices are connected by internet using a digital backbone, normally Ethernet or what we call IEEE 802.3. Similarly, internal aircraft communication also happens through a data network. This data network is called Aircraft Data Network or ADN. This is a typical communication backbone of an commercial transport aircraft. There are several features for an aircraft communication backbone. The network is primarily used for flight control, that is controlling radars, wings, and fuel injection, engine, landing, etc. are called flight control, or what we call as fly-by-wire system. Second is avionics. Earlier days, the pilot used to see all the displays, measure, instrumentation, etc. in analog. Now everything is digital. So this electronics in electronics in aircraft is called avionics. So this is the second main use of the aircraft data network. Third one is of course the other communication requirements of an aircraft like intercom, entertainment, etc. So mainly a networking backbone, a networking system inside the aircraft has to serve these three main purposes. Of course, the first two should be highly deterministic. The third may not be so. The general requirement for an aircraft data networks are as follows. Safety. In an aircraft, when it is flying, the network should be very safe, reliable, available. That means it can't fail. There should be no scope for failure. So there is zero tolerance approach towards aircraft data network. And of course, redundancy should be there. That means at any given time there should be two end system at service. Suppose one system fails, the other system will take care and do the job. Performance. The speed of operation should be much faster because the flight also happens fast. So in order to change the direction, other things, the communication should be much faster, unlike other requirements. And manageable bandwidth, low data latency. The speed is related to data latency also. Bus capacity. That means how much data you can transfer between different nodes and in system. You should have enough bus capacity. That's why in the earlier days they are using ARINC 4 to 9, ARINC 6 to 9 kind of point-to-point protocols. But since this bus capacity is very less in these protocols, nowadays AFDX is coming into the market. AFDX is a profiled version of IEEE 802.3 internet-based Ethernet protocol, particularly implemented for aircraft data networks. Of course, one more general requirement is physical aspects. It should be having electromagnetic compatibility. It should be airworthy. These are all the general requirements for an aircraft data network. Let me give some more introduction about my project. Since the airline industry is rapidly developing and the fuel cost is also increasing, the economy aircrafts are coming out. We need to reduce the cost. So aircraft OEMs are coming up with advanced optimized architectures. That's called IMA. That is integrated modular avionics architecture. This kind of architecture is mainly implemented in modern aircrafts like A380, that is largest aircraft, A400M, etc. A remote data concentrator is a device which is something like a what we, in conventional terms, in layman's term, like a data logger. Many sensors or instruments are connected to that one. It concentrates the data and sends to the main flight computer. Otherwise, each and every network element, each and every sensor need to be connected directly to the flight control computer, which will be bulky, as well as a single failure will lead to disaster. So RDC converges the aircraft subsystem sensor data and retransmits the same using global bus like AFDX. The AFDX network connects the RDC and rest of the processing computers. Using the low maintenance repair and overall costs can be reduced. That's the main advantage of AFDX. Since it's not a point-to-point connection, it's a loop meshed connection. So for a RDC kind of implementation, AFDX kind of protocol is much suitable. AFDX is fully implemented only in A380 and B787 aircrafts, and other manufacturers all over the world are trying, even including India. So what's my project scope? Let me explain. The main scope of the project is to develop an Avionics full duplex switched Ethernet protocol stack for transmission and reception of AFDX messages in Linux. I choose Linux because Linux is an open source operating system. It involves very less or no cost of development because the kernel is free. It's a PC based development. Only needs a network interface controller card, and extensive community support is available for Linux OS. It's much suitable for a student project. So I made two implementations. One is two protocol stacks running between two PCs with Linux operating system, and one personal computer with developed protocol stack connected to an aircraft test equipment or automatic test equipment. Third one is PC to an ATE through a switch. This is not a part of my project, but anyway I have implemented and tested this one. AFDX, some more introduction I would like to give. AFDX is a common communication system used for modular avionics architecture. It is this protocol is defined in ARINC 664 part 7. AFDX is specific implementation of 664 part 7 with a profiled version of IEEE 802.3 network, which you call it Ethernet. Main features of AFDX are redundancy, determinism, high speed performance, and switched and profile network. We'll see one by one what this means. It's a 802.3 standard Ethernet stack, modified one. It provides robust partitioning, highly deterministic. It contains major parts: end system, AFDX, and virtual. Some of the parameters of AFDX, let me explain. Determinism. The AFDX network delivers determinism through change in restriction to the Ethernet. Means we define the L max, that is length max of a data packet, the order of the data packet, and it always has physical dual redundancy. Always there are two end systems in every node. Virtual links are unidirectional links with a bandwidth allocated, a particular bandwidth allocated to a particular end system with a particular length maximum, that is length of the message is also restricted or defined. So let me just show an animation of how the shaping of a AFDX message takes place. Let us say at the first back value, that is the bandwidth allocation gap, there is a message ready. It gets transmitted, and in between, before the back completes, there is the second message ready from the same end system or a sensor. It won't be transmitted immediately, unlike an IEEE 802.3 Ethernet. It will be skipped and transmitted from the starting point of the next bag value, as shown in this one. And similarly, now you see from that bag value, it is not at the start of the packet, is not at the start, so it will be skipped and delayed further. So by this arrangement, you can see this bag value, this bandwidth allocation gap. So this much of bandwidth has been allocated to this end system, this much has been allocated for the same end system next message. So you cannot overlap two messages within a bag. So by this determinism is being maintained. This is a virtual link concept. It's a unidirectional link between different end systems. There can be many receiver, but only one starting point, as shown in the picture. And redundancy. You see, there are two senders and two receivers through two independent switches. So, in case one fails, suppose this fails, through this it will reach. That's why always in case of failure of one route, the second path will always deliver the message. So this is the AFDX frame format. It's much similar to the IEEE 802.3. There is a preamble, start frame delimiter, destination address, source address, type, IP structure of 20 bytes, UDP structure, and then AFDX payload. Maximum 1471 bytes are allowed, and the padding in case the data is less than 16 bytes, it will be padded so that the minimum and maximum protocol requirements are met. And there is this sequence number, which is the specialty. This is the additional feature of AFDX to the IEEE 802.3 frame. And there is of course the 32 bit polynomial based frame check sequence CRC, and the OS will take care of the 12 byte interframe gap. So how I constructed my made my packet of AFDX frames, I am just explaining through this animation. So initially there is a sensor data, then I am enveloping that with UDP header, checksum, etc. Then using raw socket, I am adding AFDX message with UDP and passing to IP level. Then 20 byte of IP address with checksum, etc. has been added. Then it will be injected to layer 2 directly in the NIC card. Physical layer chip in the NIC card will transfer through the wire. At the receiver end, it will be received. The physical layer preamble and other bits are stripped off. Second thing, at the layer 2, the MAC header will be stripped off. IP header will be stripped out at the network layer. At transport layer, UDP header will be stripped off. Finally, what we get is raw data which we have sent from the sender node. This is how I do the packet sending and reception. And the socket I am adding IP, UPAD and other headers and appending the entire frame and sending through transmission. In case of reception, there is another part of stack. The same end system will receive. Once it has been processed, and when we want to close the protocol, the socket will be closed. Concurrently, there will be a management information base running, and any failure, etc., will be loaded in this one. And I am also implemented ICMP echo request part in order to ping the network. The entire thing will be made by kernel threads in the Linux operating system. This is my overall algorithm. This is how a 7-layer OSI model comparison of my project. Physical layer has been taken care of by the physical layer chip itself. I am not doing anything. At the data link layer, virtual links are taken over. Using packet socket, I am doing it. On network layer, I am using IP, UDP at transport layer. Sessions layer, I am not doing any coding. Presentation application layer is up to the application programmer. This is what I have done. This is what the protocol requirement of the RFC is RX 664 part 7. So this is the output of my project. This is the transmission of my formed frame. This is the output screen capture. This is the reception TX. Earlier one is TX. This one is RX. Reception screen capture output. This is TCP dump, which is similar to Wireshark, which we can use in Linux for seeing the link layer output. And so I have tested my protocol stack. This is all the tested I have conducted. Data padding test, that is less than 16 bytes I have appended, and it is the protocol takes care and makes it 16 byte. Data length test, which is protocol requirement 1471 less and various levels 0 to 1471 bytes I have tested. VL, MAC and IP I have varied this to different combinations and it is worked. Sequence number management test, AFDX tag, IP, UDP, checksum, etc. And bag value test from 2 to the power of 0 to 2 to the power of 7 I have tested. And concurrently TX, RX together in a single in system I have tested. And protocol filtering at reception end I have tested. Sequence number filtering also tested at the reception end. And ICMP ping between two pieces I have tested. A latency analysis I have tested for kernel latency for reception, kernel plus stack latency for transmission. This is for bag value of 1 and 4 milliseconds for transmission. This is the reception. Hi friends, I am P.THIRUMENI and this is combined reception plus transmission latency for stack. And these are all my conclusions of the project. A detailed analysis of AFDX protocol has been done. A feasibility study on implementation on Linux has been done. And coding in C for the all 7 layer OSI layer model has been done. A working AFDX protocol stack has been developed for Linux operating system in C language. The developed stack is checked extensively between two pieces and an aircraft test equipment. The conformity with the standard RFC RING 664 part 7 has been carried out. The Linux based AFDX stack is testified and various temporal data latency analysis has been done. The latency analysis for RX TX has been done in a limited way. Thank you friends for listening to my project details. This is P.THIRUMENI, M.TECH Embedded System Technologies, VTP Technical University. Thank you.